Alright, I now want to show you a different way to calculate partial derivatives called implicit partial differentiation. Okay, so let's say we're talking just about functions of two variables. So what you've looked at so far is to how to differentiate an explicitly defined function. Okay, so an explicitly defined function is something of the form where z equals f of xy. Z is solved for. Z is given by some explicit formula involving the variables x and y. Okay? Sometimes, instead of a function being described explicitly, the function will be described by an implicit equation of the form, we'll call this capital F of x, y, z equals 0. Okay. So here, z is the solution to the equation f of x, y, z equals 0. Every explicitly defined function could also be written in implicit form as well, in which z is the solution to the equation f of x, y, z equals 0. If you give me an x and a y, then I can solve the equation for the z at that point x, y. Okay, an example of an explicitly defined function of two variables is x squared plus y squared plus z squared equals 9, which obviously describes a radius of 3 units in 3-dimensional space. Okay, so here is my surface. Okay. If you're given an x and a y, you can solve this formula for z. An explicit formula would be z equals the square root of 9 minus x squared minus y squared. But of course, we know there's a little subtlety here in that there are two solutions for z, because z also equals the negative square root of 9 minus x squared minus y squared. The surface of a sphere cannot be described as the graph of a single function, but each hemisphere can be described by an explicit formula. So, how do we calculate partial z partial x and partial z partial y? Well, you know how to do this when z is given explicitly, but sometimes you might be given an implicit formula where it is difficult or impossible to solve for z, so in that case you need to use another method. So we're going to use the implicit formula for the sphere to demonstrate how this sort of implicit differentiation works. Okay, so again, I'm starting with x squared plus y squared plus z squared equals 9. In order to find partial z partial x, I want to think of z as being defined as a function of x, where y is a constant, and differentiate with respect to x. So, the derivative with respect to x of x squared plus y squared plus z squared is going to equal the derivative with respect to x of 9. Alright, so I'm going to have 2x partial x, which is just 1, plus the derivative of y squared is 0, plus 2z partial x. So remember, I'm considering y to be a constant and x and z to be my only variables. Of course, the derivative of 9 is 0. So now we want to solve for partial z, partial x. So I have 2z partial x equals negative 2x times 1. I'm just going to drop that. And I get partial z partial x equals negative x over z. Okay, so there is the partial derivative of z with respect to x for our sphere. So let's think about what this means in terms of the picture of our sphere. Consider that partial z partial x is a slope. So when z is very small, well, if z is small on the sphere, that means you're close to the xy plane. If z is very small, you're dividing by an infinitely small number, which will result in a very big number. So above the xy plane, you have a very steep negative slope, because you're dividing by an infinitely small positive number. And just below the xy plane, you have a very steep positive slope because you're dividing by an infinitely small negative number. So you can see the surface of the sphere is very steep near the xy plane. Near the top and bottom of the sphere, z is getting bigger and x is getting infinitely small, and there you're going to result in a very small value for partial z partial x, and the slope is less severe until, at the top or bottom of the sphere, the slope is 0. So in order to find partial z partial y, we're going to do a similar calculation. We're going to think of z as a function of y and consider x to be a constant and differentiate with respect to y. So the partial derivative with respect to y of x squared plus y squared plus z squared equals the partial derivative of y of 9. And again, I'm going to get 0 plus 2y partial y plus 2z partial z partial y equals 0. And then I get partial z partial y equals negative y over z. And of course I could describe the slope on the surface of the sphere very similarly to how I did for partial z partial x. Okay, if we compare this method to what I would get if I differentiated using the explicit formula. Okay, so I have two formulas for z. I have z equals the positive square root of 9 minus x squared minus y squared, and I have z equals the negative square root of 9 minus x squared minus y squared. Let's just consider the positive square root for the moment and calculate partial z partial x. So partial z partial x equals 1/2 9 minus x squared minus y squared to the negative 1/2 times negative 2x, which equals negative x over the square root of 9 minus x squared minus y squared. And if you notice, the bottom, the denominator of that fraction is z, so I get negative x over z, which is of course the same thing that I got when I took the derivative implicitly. Now in this case, neither method was really more difficult than the other, but if you have an equation where you cannot solve for z as a function of x and y, then implicit differentiation is obviously the way you need to go. All right, let's do one more example. All right, here we go. So we are going to suppose that z is the implicitly defined function given by the equation zx squared plus y squared plus xyz squared equals 0. And we are going to find partial z, partial x. Okay, I'm going to need to use the product rule here. So the derivative of z is 1 partial z partial x times x squared plus z times 2x partial x partial x. The derivative of y squared is, of course, 0. And then here, I'm going to group this just like this. The derivative of xy is y partial x z squared plus xy times 2z partial x equals 0. Okay? And now I'm going to keep the things that have a partial z partial x on one side of the equation, and I'm going to move everything else over to the other side. So the first and last terms have a partial z partial x. So I'm going to keep them on the left side, and I'm going to factor out partial z partial x, which gives me x squared plus 2xyz. Moving everything else over to the other side, and remembering that partial x is just 1, I'm going to have negative 2xz minus yz squared. And lastly, I'm going to divide to get partial z partial x by itself, and I get negative 2xz minus yz squared over x squared plus 2xyz. So there is my partial derivative of z with respect to x found using the implicit differentiation method. Of course, in this particular equation, you could have solved for z using the quadratic formula. Of course, that would have been incredibly messy and much more difficult. But let's just say this had been a z and this had been a z to the 5th, then you never would have been able to do that, and implicit would have been the only way you needed to go. All right. Good luck. Enjoy your homework.